Hi there, and welcome to Mr. Morgan's Math Help. We're on Algebra 1, Unit 1 on sequences for Lesson 8 called What Does It Mean? Again, this is part of the Open Up resources here, so if you have another textbook, there are other videos for other textbooks that have different Unit 1s in Lesson 8, so make sure you're in the right place. All right, as always, these are going to be the homework solutions after today's class and lessons, and ideally you've done the homework and given it some try a little bit, and now you're here to watch and see how'd you do and are you really understanding things. That's the idea behind these videos here. All right, so first of all, it says use the Venn diagram to compare and contrast arithmetic and geometric sequences, words that I can't spell very well. All right, so for the arithmetic sequences, what you're going to have is you're going to have common differences for these ones that are added or subtracted. Right, you're going to have things like plus 2, minus 3 in terms of what's happening between the terms. Okay, for the geometric, we have common, it's not differences, if you recall, it's common ratios. Okay, that is multiplied to make a new term. Okay, for both of them, you need to have some sort of initial value, a starting point, and then there can always be many representations, right? Different ways of showing that there. Okay, so for the arithmetic, we're looking at adding and subtracting for the change that's taking place there. And for geometric, we're multiplying, and that's the kind of change that's taking place there. Okay, this one is going to be the ratio side, and this is going to be the difference side. All right, moving forward. So for this first one, or this next one here, it says for each representation in problems 2 and 3, select all items that connect to it. So we want to look at the items that connect, for example, to number 2, where we have this table. We can see that we are decreasing by 10, right? Again and again, decreasing by 10. And so we want to take a look at what are my options here for which things could be showing in this box here of options, showing a decrease of 10. Okay, so when I look at, well, let's look at this before we move on. Number 3 is also going to be, it says Jose is studying the growth of the economy. He believes that the rate of growth, so the rate of growth will be 2% for the next several years, has a current value of 22 trillion. How many years will it take to double the value? Okay, so what we see in this one is we have a rate of growth, so we're increasing by 2% a year, and we have a starting point of $22 trillion. Okay, so just comparing the two things. Here we can see that we have an arithmetic sequence here. Make sure I'm spelling it right here, metic sequence here because we're subtracting, right, minus 10. Here we seem to have a geometric sequence because I'm multiplying by 0.02, which is 2%. So now let's take a look at my options. For A, we can see we have something taking place, and I'm multiplying 22 by 1.02 t. Okay, just in terms of just some numbers here, that 22 seems to match with our 22 trillion. 1.02 would be like multiplying by 102%. We know that our multiplier is already going to be 2%, so for 102%, that would become 1.02. So A seems to go with number 3. B says Alex is borrowing $10 from his mom. So borrowing $10 means, in a sense, you owe money, right? You owe money. Yes, he might have money, but he also owes it because he's borrowing it. So we can see a 10 decrease happening over here. So I would say for number 2, B goes best with that one. For C, we can see minus 10 to the n minus 1. Okay, what this represents for us here is we can see this is our first term, right? That is our f of 1, or in this case here, our g of 1, right? Our first term. And we can see that our decrease, our rate is here, minus 10. And this becomes what we use for our arithmetic sequence there. So we can say that C also goes there. For D, we have a table, we have a graph here. We can see it's decreasing, so it's going down this direction. So we know it's going down. So it's either going to go with this one, but it can't go with this one. This one's increasing. So in terms of what it's doing, we would say probably D makes the most sense. It's going down. We could also take a look and notice that at 1, it's about here, about halfway, which is about 10. And at 2, it's at 20. And these are negative, so those values do match. For E, we can see that it's starting here at, there's 20, a little bit above 20, so perhaps 22, and we can see it's increasing. So E matches number 3 for our 22 and increasing. And finally, F, we can see in terms of values, we can see that it is increasing. Each one's going up, right? I'm going to draw my arrow like this, but we can see it's increasing each time, getting larger, which matches number 3. So we would say B, C, and D go with number 3, and A, E, and F go with number, B, C, D go number 2, and A, E, and F go number 3. All right, next question. Each of the tables given represents an arithmetic sequence. Find the missing terms in the sequence, show your method, and create the explicit and recursive equations. All right, so let's do this one here. All right, so what I can see here is we know that it's, first of all, it does say it's arithmetic. That helps me know that I'm either going to be adding or subtracting each time. So keep that in mind as you're looking at the solutions here. So I'm going to be adding something to get to that term and then adding that same something to get to that term. So my strategy was this. I said, well, whatever I'm going to do, I'm going to do it twice. So let's say, what's the difference between 12 and 3? Well, 12 minus 3 is going to be equal to 9. So if I take the 9, I know that I have to add the 9, well, not 9, but the values inside the 9, 2 times. I'd make 2 little jumps there. So I'm going to divide 9 by 2 to indicate my 2 little arrows, right? Arrow 1 and arrow 2. I need to split the 9 up 2 times. So 9 divided by 2 is 4.5. So it tells me that I'm adding 4.5 each time. So 3 plus 4.5 is 7.5, and 7.5 plus 4.5 is 12. So that becomes what I'm adding, okay? So this one has, we're adding 4.5. So in terms of a recursive, we would say that f of n is equal to f of n minus 1. And then what are we doing? We are adding 4.5. And this is true when what? When f of 1 equals 3. So I want to include that so we know where our starting point is going to be. In terms of the explicit formula, what we would say here is that f of n is going to be equal to, okay, what's it going to be equal to? Well, it's going to be equal to our rate of change, 4.5 times n, and then we want to say what it's equal to is going to be also to, in a sense, our starting point. And the way we can find the starting point here is we could subtract 4.5. And so if you do 4.5 minus 3, we get 1.5, and we know we started at a positive, so we're going to end up with a negative. So we'll subtract 1.5 for our explicit formula there. Okay, so that's number 4. For number 5, again, we're adding. I'm going to add 1 time, 2 times, 3 times this time. So my difference is 26 minus 2 is 24. Let's take that same 24 and divide it 3 times so we can see that the difference is going to be split up nicely by 8. I'm adding 8 each time I make a turn or make a hop. So 2 plus 8 is 10, 10 plus 8 is 18. Okay, so my recursive, first of all, is f of n equals function of n minus 1. And what are we doing? We're adding 8. For my explicit, I'm going to say that f of n is going to be, sorry, down here. This works when f of 1 equals 2. So back to explicit, f of n is going to be equal to our change, our rate of change, 8n. And then I need to say, well, what happens at the 0 point here? What happens at 0? Well, subtract 8. Negative 8 plus 2 is a negative 6. So we'll say minus 6 goes there. Okay, so that's what's taking place there. All righty. Okay, let's take a look at the next one. Okay, we're still adding or subtracting, so we know we're going to go there, and to there, and to there. All right, so let's find our difference. 24 minus a negative 3. When I subtract a negative, it's like adding, so that becomes 27. I have 3 moves here, so 27 divided by 3 is equal to 9. Now I'm decreasing, so I'm going to subtract 9 each time. Subtract 9, subtract 9. So 24 minus 9 is 15. 15 minus 9 is 6, and 6 minus 9 is negative 3. So the recursive is f of n is equal to our previous term, n minus 1, and then our change, minus 9. Our explicit, and this, takes place when f of 1 equals 24. There's our starting point there. And our explicit is going to be a little different, right? That's going to be that f of n is equal to, in this case here, it's our rate of change, negative 9n, and then our starting point. So if we add 9 to 24, we would say it's 33. Now, is there another way of looking at that? Well, there certainly could be. Let's look at another way of writing this same explicit formula, okay? We can also say that the explicit's going to be, in our case here, the starting point, which would be 24, right? F of 1 is 24, minus our rate of change times n minus 1. Now let's see, if we were to multiply this out real quick and use the distributive property, I would say, oops, that's not what I want to do, sorry. Let's go back. I don't know. So let's go back. So 9 times n minus 1. Okay, so if I use the distributive property here, I would say, I would go 24 there, minus 9 times n is minus 9n, and negative 9 times negative 1 is a positive 9. So 24 plus 9 is 33, and we still have a negative 9n, or written the other way, negative 9n plus 33. So we can see this matches this one here. So another way of writing this explicit formula, okay, this is why it's important to have a starting point here, is that we use the starting point to become the first term, and then we use that rate of change to become this next part, and then the n minus 1 is part of the explicit formula. Okay, so let's back up real quick here and look at this one over here. All right, what was our starting point for number 5? Well, our starting point was at 2. So we could say f of n equals 2, and our rate of change is 8. So we would say plus 8 times n minus 1. Now, if we're not sure if that works or not, let's just double check. 8 times n is 8n, and then 8 times negative 1 is negative 8. We have 2 there. 2 plus negative 8 is going to be a negative 6, and that matches. Okay, so what we can see is that when we know our starting point, we can use that term, we can use our rate of change here, and we can write an explicit formula. Okay, so keep that in mind. That's going to start coming up a few more times here. All right, next one. Identify the type of sequence and then determine the recursive and explicit equations for each sequence. If the sequence is not arithmetic or geometric, identify it as neither and don't write the equations. All right, so let's do this here. So for the first one, we can see we're going from 5 to 9. That looks like adding 4 to me. 9 to 13 is adding 4. 13, 17 is adding 4. So because we are, whoops, too far. Because we're just adding 4 each time, we would say that's arithmetic. Okay? For our recursive, we could say that f of n equals the previous term, f of n minus 1, and then the rate of the change. Okay? Now, we also have here a couple things. Let's mark them for us. We have the rate of change, and we have the first term. So let's try the other method for the explicit. We could say that f of n is going to be equal to, in this case here, remember back over here, what did we say? We said that our starting point became the first term, okay? So our starting point in this case is 5, so we could say 5, and then we took the rate of change plus 4 times n minus 1. Now that's the new way of doing it, okay? Our other way of doing it before was to say the function was equal to, and what we said before is we said, well, our function was going to be equal to, in this case here, we would say our rate of change for n, and then we would often try to go back and figure out what went right there, right? And if you recall, we would do this. We would go minus 4, so 5 minus 4 is 1, and we would say plus 1 to figure that out. So we were doing a little bit of like a sneaky math to figure that out. Let's see, if I was to expand this here, I'd have 5 plus 4n minus 4, and when you rewrite that, you have 4n plus 1, exactly the same. So I just wanted to show you this again because this is the way you'd really go about writing the explicit equation without having to do this funky little subtraction thing to find the first value or the value at 0, okay? So you do end up in the same spot. So keep in mind there are two ways of looking at that one. All right, the next one. We have 60 to 30, so it looks like we're subtracting 30. 30 to 0, subtracting 30, and still doing it. So this is arithmetic, no problem there. For our recursive, we're going to say f of n equals the previous term, f of n minus 1, and then our rate of change, which is minus 30. Okay, doing okay so far there? Now, for the explicit, let's try the new method. I have my starting point here, and I have my rate of change here. So we're going to say that f of n is equal to our starting point minus, I'm saying minus because our rate of change is 30 times n minus 1. Okay, does that work? It certainly does. Could you write it a different way? You certainly could. You could also write that it's going to be equal to, in this case here, we'd have to say our rate of change, which was negative 30, right? Negative 30 n, and then we have to figure out where we're going to start from. So I'd have to go back this way and actually add 30 to 60 to say I'm going to start from 90. We would say plus 90. So both of those are fine ways of writing it. Again, remember back on our very first question with the Venn diagram, it asked you, well, what goes in the middle? Well, there are many representations. And what you're seeing here is that there are many representations here, different ways of writing this out. These are two ways of writing the same thing. All right, next one. Here, we're going 60 to 30, so that could be minus 30, or it could be times a half. Let's look at the next term, 30 to 15. Well, that's not minus 30, so we're going to stick with times a half. So we're multiplying by a half. Because we're multiplying, this is geometric. So now let's go with our recursive equation. our recursive equation is going to be f of n equals f of the previous term times our rate of change. So times 1/2 in that case there, times 1/2. Now, for our explicit equation, all right, we got to think about this one here. Our previous way of looking at it was this. We would say that function of n, or f of n, was equal to, and we would always look at this and say, well, what we did is we said we would take our, kind of our starting point, right? We would take our value there, what was happening again and again, 60, and we're going to multiply it by 1/2, which is our rate of change, to the n minus 1 power. Okay? So does that work? It certainly does work. It works every time for us, so no problem. That's going to work for us. Okay? So we can leave it like that, and we're good. Now, the way we used to figure that out was with the table, if you recall. We'd make the table like this. We'd say 1 was 60, 2 was 30, 3 was 15, and we kind of looked and said what was happening. This was 60 times nothing. This was 60 times 1/2. This was 60 times 1/2 times 1/2. So basically we were saying, well, we wanted to make the 60 the common thing, which is there, and that 1/2 became what we were doing each time, right? In the first one, we don't want 1, so it became 1 minus 1 is 0, which means that's equal to 1. So this became just 1. So 60 times 1, we're good to go. Or 0. Yeah, the whole thing became 1, sorry. So that's what we were doing before to figure out what that would look like. Okay? And that's fine. When we're talking about geometric, that works just fine. You can certainly do that. No problem whatsoever. All right, looking at the black tiles. Black tiles. We have 1, and then we have 2, and then we have 4. So what's happening from here to here? I'm multiplying by 2, multiplying by 2. Because I'm multiplying, this is geometric. So our recursive will be f of n is equal to f of n minus 1 times 2. Okay? Now, for our explicit equation, what we would say is that f of n is equal to, in a sense, we could say our starting value times the rate of change to the n minus 1 power. Of course, that could be rewritten without the 1 right there. You don't need a 1, and just say 2 to the n minus 1 power. All right, and number 12, from 4 to 7, it's plus 3. 7 to 12 is plus 5. 12 to 19, plus 4. That doesn't make any sense at all, so we would say this is neither, just random numbers, so you're not going to have a recursive or an explicit equation at all. All right, that's it for the day. Hope that helps you out quite a bit. You're getting the hang of this here. A couple more lessons to go in this unit. Thanks for being here with us, and we will see you next time.